Ever wonder why your phone's weather app might say 70% chance of rain instead of just it'll rain? Or why a doctor might say, I'm pretty sure, but let's run more tests? That's uncertainty quantification, teaching machines to say, I'm not 100% certain, but here's how sure I am. Imagine an AI analyzing a molecule and declaring, this is toxic, but how does it know? Traditional AI models like graph neural networks, GNNs, excel at spotting patterns in complex data, social networks, road maps, or molecular structures. But they're like a magician's trick. They produce results without revealing how they got there. This is where uncertainty quantification becomes critical. Think of it as a detective who doesn't just solve a case but also says, I'm 90% sure this suspect is guilty because of these fingerprints, but there's a 10% chance I missed something. For AI, this means predictions aren't binary. They're layered with confidence levels, so we know when to trust them and when to double-check. Enter GraphFNP, a breakthrough method that tackles this head-on. Here's the twist. Instead of giving a single answer, GraphFNP models probabilistic embeddings, which are like clouds of possible explanations. If a molecule is predicted to be toxic, the model might say, there's an 80% chance this is toxic, and here's why, highlighting specific chemical groups or structures it's focusing on. But how does it know what to focus on? That's where latent rationales come in. These are the hidden patterns in the graph that drive predictions. For example, in a molecule, maybe a nitro group, No2 is the key clue. GraphFNP decodes these patterns, making the model's thinking visible. The magic happens with a stochastic correlation matrix, which acts like a dynamic web linking clues to real-world data. It's like a map showing how different parts of a molecule interact, helping the model weigh its confidence. Plus, a graph-generative model rebuilds these patterns, letting us visualize and verify them, so we're not just taking the AI's word for it. And the results? In tests across multiple datasets, GraphFNP outperformed traditional methods by not just being more accurate, but also by giving clearer, more honest explanations. For instance, when analyzing molecules, it highlighted known toxic groups like NH2 or NO2, aligning with scientific knowledge. When uncertain, the model admitted it, rather than forcing a guess. Let's start with the problem. Traditional AI struggles with data that's connected, like social networks, molecules, or neural pathways. These are graph-structured problems, where relationships between data points matter as much as the data itself. But standard AI, it's like a chef who knows recipes, but can't tell if the ingredients are fresh. It misses the connections that make the whole picture make sense. Enter graph neural networks, GNN, AI that sees those connections. But even GNNs can be shaky when it comes to uncertainty. That's where GraphFNP steps in. It's like giving AI a built-in confidence meter and a detective's notebook. By combining Bayesian methods, which quantify uncertainty, with stochastic processes, math that handles randomness, GraphFNP lets models not just predict but explain their reasoning. Why does this matter? Imagine a drug discovery, AI suggesting a new molecule. If it's overconfident in a wrong prediction, it could waste years of research. GraphFNP solves this by measuring two types of uncertainty. 1. Model level, how confident the AI is in its overall guess. 2. Data level, how reliable the input data is. It's like a student who not only answers a math problem but also shows their work, so you can spot mistakes. GraphFNP also makes AI more explainable. Think of a fraud detection system flagging a suspicious transaction. How does it know? GraphFNP traces the decision back to specific connections in the network, like a detective pointing to a suspect's alibi. Techniques like graph normalizing flows act as a reverse engineer, showing exactly which parts of the data influence the outcome. Researchers tested GraphFNP on real-world challenges, like analyzing molecular structures and text-based graphs. The results? Better calibration. Predictions are more reliable, avoiding overconfidence. Think of a weather app that stops claiming 100% rain when the sky is clear. Transparency. The model highlights key connections, like pointing out a critical chemical bond in a molecule. Robustness. Even when parts of the model were tweaked, it stayed accurate, like a car that keeps driving even if a tire loses air. This isn't just about fancy math. GraphFNP is paving the way for AI that's safer, more transparent, and truly trustworthy. By combining uncertainty quantification with interpretable explanations, models like GraphFNP turn black boxes into transparent partners. Whether it's drug discovery, social network analysis, or safety checks, this tech could revolutionize how we use AI in high-stakes decisions. Thanks for watching. If you want to dive deeper into the research, check the links in the description. Stay curious, and we'll see you next time.